Now, chapter 7, we've done a chunk of already. When we did empirical formulas back in chapter 2, it actually had its roots here in chapter 7. The reason we did it then is because chapter 2 and chapter 7 have a lot in common. Chapter 7 is basically an extension of the calculations in chapter 2. So if you understood those calculations, you're going to do pretty well in this chapter because it's just kind of the next logical step. But that's more for Friday when we get to that step. For today, we are going to focus on the chemical equation itself. And for that chemical equation, we are going to focus on the kind of the guts of it. What makes it what it is. So we know that chemical equation basically tells the story of a chemical reaction. We start with products. Those products rearrange themselves, convert themselves through a chemical change into, we start with reactants. Those reactants react and convert themselves chemically into products. And we've got the reactants here on the left side, and we've got the products here on the right side. Now, often chemical equations will have phase designations on them. And here's kind of your comprehensive key to what those mean. So the first three you already should know. S for solid, L for liquid, G for gas. You've been hearing about those particular states of matter since you were probably about 6 years old. Nothing's really changed about any of those. We're just designating them in chemical equations here. AQ might be something you're not as familiar with. AQ stands for aqueous. Aqueous meaning that whatever that substance is, it's dissolved in water. So if we're looking for it visually in the chemical equation, in the chemical reaction as it's proceeding, we may not necessarily see it because it's been dissolved in the water. But if we were to boil off the water, sure enough, it would be there when we did so. Now, that last state of matter is going to become very important for us in chapter 8 when we look at reactions that occur in solution. So we'll kind of leave that right there for now, but understand we're going to see a lot of it coming not that far away. When it comes to chemical equations themselves, we have to understand that, like anything, a chemical reaction has to obey the law of conservation of mass and the law of conservation of matter. And for those reasons, those chemical equations need to be balanced when they are written for us. So if I look at this chemical reaction that is on the slide here, sulfur reacting with oxygen to make sulfur dioxide. I can look at this in a variety of different ways, both from a matter perspective and a mass perspective. And what I should notice is that it always comes out even if I compare the right-hand side of the equation and the left-hand side of the equation. From a particle standpoint, I've got an atom of sulfur reacting with a molecule of oxygen to make a molecule of sulfur dioxide. From a mole ratio standpoint, I've got one of each of those substances. From a mass standpoint, I can see that my product equals the sum of my reactants. There's my law of conservation of mass. If I look at it from an atomic standpoint, I have one sulfur atom over here, one sulfur atom in this molecule in the products, two oxygens over here in the reactant, two in this product compound. So everything is conserved on both sides. That's where a balanced chemical equation becomes important. Now, the question in the task in front of us is how to actually go about balancing those equations. And so hopefully your skill builder yesterday helped to kind of ferret out some of these details. But if you're still struggling with the concept, let me offer just a few things that might help. So first of all, there is a methodology that we can use, especially for when we are getting just started. And honestly, I still use this sometimes if I have something really complicated and I just want to organize myself. It's the atom economy method. Basically, I divide the reaction in half. I count up all the atoms on the reactant side, all the atoms on the product side, and I just do an inventory every time I add a coefficient to the equation, knowing that eventually everything will even out on both sides. Now, as you get better and better at this, and we'll kind of develop some things that you can start to look for along the way, the atom economy method isn't going to be necessary all the time. You can be able to do some inspection-based balancing, where you can just look at it and say, oh, okay, I get it. This side needs another oxygen, and this side needs another iron, and it all balances out. Now, to transition from that kind of very rigorous method to the easier, faster method, there are some things that we can keep in mind that help us. First of all, one thing we can look for are what I call ionic clusters. In replacement reactions, where we have polyatomic ions, it is very common to see the same polyatomic ions on both sides of the equation. And when we have that circumstance, rather than splitting them up and saying, okay, nitrate has 1 nitrogen and 3 oxygens, I can keep it together, because if it's on both sides, it's going to stay together. So especially for replacement reactions, this is a useful tool to cut down the number of things that we need to keep track of. Similarly, if my chemical reaction has a compound that has multiple subscripts on it, that can be really useful to us. We could actually use that as a guide to help us figure out how to balance the other side of the equation. Because usually when we have a product like that, it's easy to see usually where the cobalt comes from, where the sulfur comes from. And I can apply those coefficients based upon those subscripts. And then finally, if I have elements that are in multiple compounds, I'm going to try to save those for the end. Usually what we're talking about here are things like oxygen and hydrogen, probably 2 of the most common elements that we run into in chemistry. If it's in multiple compounds, in multiple products, let's leave it alone. We'll save it for last. And hopefully by the time we get around to it, it becomes pretty easy to see what we need to do. So let's put some of this into action with some example problems. So here's our first example problem. When the following equation is balanced, the coefficients are what? So right away, we can see that oxygen is going to be a problem for us. I've got oxygens on the left-hand side. I've got oxygens in multiple products on the right-hand side. So if you think about that third tip, this is where we would apply that third tip. We're going to save oxygen for the last. Hopefully it works itself out. We can also utilize our idea of the subscripts. If I look at my carbon compound, I can see that it's got multiple subscripts, an 8 and an 18. I can use that to try to influence my balancing on the other side. So let's set up our atom economy real quick. I've got carbons, I've got hydrogens, and I've got oxygens. On this side, I have 8 carbons, 18 hydrogens, and 2 oxygens. On this side, I have 1 carbon, 2 hydrogens, and 2 plus 1 for a total of 3 oxygens. If I use this compound as a guide, what I'm going to do is the carbon is going to influence the coefficient on carbon dioxide, because that is the only place we find carbon in the product. So I have 8 carbons over here. I'm going to turn that into 8 carbon dioxides. And the hydrogen is going to influence my hydrogen in my water. So I have 18 hydrogens. Each water has 2 hydrogens, so 9 times 2 gives me the 18 that I'm looking for. Now that I've changed coefficients, I need to change my accounting here. So I now have 8 carbons, 18 hydrogens. So far, so good. And we've gone to 8 times 2, so that's 16 plus 9, total of 25 oxygens. Okay, not bad. We've solved everything except for oxygen. The only problem we have now is to get oxygen to 25, I have to use a number that is not a whole number. Now, there's 2 ways I could go about this. One of them is I could recognize, okay, the number I'm looking for here is 12 and a half. 12 and a half times 2 gives me my 25. From a pure standpoint of balancing, yeah, I'm balanced. Problem is, if I'm looking at this from a molecular standpoint, how on earth do I get 12 and a half oxygen molecules? The answer is, I can't. Now, if I'm looking at this on a macroscopic scale, on a molar scale, 12 and a half moles of oxygen, yeah, I can measure that. Whatever 12 and a half times 32 is, I can measure that number of grams of oxygen. But if I'm looking at the molecular scale, I have a problem. So to solve that problem, I'm going to have to do very similar to what we did with empirical formulas. How do I get rid of a half? I have to multiply everything by 2. So when I multiply everything by 2, change our color here. 2 times 1 is 2 for the octane. 2 times 12 and a half will give me 25 for the oxygen. 2 times 8 will give me 16 for the carbon dioxide. 2 times 9 will give me 18 for the water. If I redo my inventory, 2 times 8 is 16. 2 times 18 is 36. 2 times 25 is 50. On the product side, 16 carbons, 36 hydrogens, and now 32 plus 18 for a grand total of 50 oxygens. Everything is now balanced. I have a balanced chemical equation. Hooray for me. So when it comes to balancing equations, these kinds of problems are kind of as complicated as they get, because you end up having to do some multiplication at the end to get it to balance out. into a format that you can use. Let's take a look at another example. Here I've got Fe3O4 turning in hydrogen, turning into iron and water. We're going to do the exact same thing. Split it down the middle. I've got iron, oxygen, and hydrogen. Three irons, 4 oxygens, 2 hydrogens on the reactant side, 1, 1, and 2 on the product side. Now, once again, here's where our multiple coefficients thing, or excuse me, our multiple subscript thing is going to help us. Our iron oxide compound has multiple subscripts. We will use those subscripts to influence the coefficients on the other side. So 3 irons in the compound means 3 irons in the product. Change my iron from 1 to 3. 4 oxygens in the reactant mean I'm going to need 4 waters to balance them out. Now, in the process of balancing out the hydrogen or the oxygen, I've disrupted the hydrogen. My hydrogen went from 2 to now it's 4 times 2, 8. But luckily, hydrogen on the other side, I can quickly fix that to get it to balance out. My atom economy shows me that the reaction is balanced. And then in this case, it wasn't that difficult to do. Went relatively easily because, well, the math wasn't too terribly difficult. And if we look for those little hints, that usually helps things out because usually we can use at least one of them along the way. Let's do another example. Here I have potassium sulfate reacting with barium chloride to make potassium chloride and barium sulfate. So in this case, we don't have multiple subscripts, but what we do have is an ionic cluster. We should be able to recognize that the sulfate ion is common to both sides. So instead of tracking sulfur and oxygen individually, when we set up our accounting here, we're going to keep the SO4 clustered together since it is the same on both sides. Now doing that, I can see I have 2 potassiums, 1 sulfate, 1 barium, 2 chlorines. On the flip side, I have 1 potassium, 1 chloride, 1 barium, 1 sulfate. The wonderful thing about these kinds of reactions is they're usually pretty easy to balance because it's pretty easy to see what's not balanced, and usually what's not balanced is in the same product. So with one small adjustment, in this particular case, that was all that we needed. All right, any questions before we try a couple on our own? Okay, so this is a fill in the blank question. I've got 2 chemical reactions for you to balance here. What I want you to do, balance the equation. So, for example, every single blank needs to be filled. It's not going to let you submit unless all of them are. If you would leave one of them blank because it doesn't need a coefficient, remember that the coefficient there is 1. So put a 1 in the blank. All right, walking around, it looks like most of you are on the right track, if not having it outright. The key to the first one was, again, using that double subscript. You should have been able to see we needed 5 carbon dioxides and 6 waters to do it. If you did the math correctly there, that meant that there were 16 oxygens over here. So we needed 8 on that side. So this was a case where we didn't have to double anything up. The numbers worked out for themselves. Same thing over here. The double coefficient should have led us in the right direction. I needed 3 oxygens and 2 nitrogens to balance this out. So initially you may not have gotten exactly that, but again, if you recognize that you had a situation with a 3 and a 2 there, you're going to have to come to the lowest common multiple between them. So you could have gone that direction. You could have also gone to the half-step direction. This is 1 1/2. That would have balanced out the oxygens and the nitrogens, and then realize that you could double everything up. Make that 2, 3, and 2. All right, any questions about equation balancing before we move off of it? Okay, so with the remainder of our time, and we don't have a ton of it, we're going to go through the 5 main types of chemical reactions. And why these are important is because they allow us to do 2 things. Recognizing these allows us to help predict products of reactions. So get an idea of if I put this and this together, what should happen? And it also can give us some insights for looking out for certain things to help us balance the equations themselves. Because replacement reactions can be balanced by kind of the same process, but slightly different than combination, decomposition, and combustion, which tend to be very, very focused on that double coefficient, or the double subscript, double coefficient kind of method. So the 5 types are these: combination reactions, sometimes referred to as synthesis, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. So what we're going to do is we're going to just take a look at each one of these in turn to help you recognize them appropriately. So let's start first with the combination reaction. In a combination reaction, we have a single product being formed from 2 or more reactants. So generally speaking, we've got 2 reactants, sometimes more, forming a single product. Common examples of those would be things usually forming forming larger molecules out of smaller ones. So hydrogen and chlorine come together to make hydrogen chloride. Water and sulfur trioxide come together to make sulfuric acid. Magnesium and oxygen come together to make magnesium oxide. Usually elements, sometimes small compounds, coming together to make something larger. And so here's another example. Here we have the gaseous product, dinitrogen pentoxide. When that substance comes into contact with water, this is one of the ways that we can create nitric acid. Decomposition reactions, on the other hand, are pretty much the opposite of synthesis reactions. In decomposition reactions, we have a single reactant that, due to some stability issue, whether it's just its natural instability or we force its instability by heating it, charging with electricity, doing some sort of manipulation to it, it breaks apart into simpler substances. Sometimes those substances are elements. Sometimes those substances are small compounds, like little gases. When we see the Greek letter delta here in a chemical reaction, that is a sign that we are talking about something being heated. That's what that symbol means. And that is a very common mode of decomposition. So again, the format here, we've got a single reactant breaking up into multiple products. Common examples of that would include water decomposing into its hydrogen and oxygen. Now, this is not done with heat. You can heat it as much as you want. It's not going to break down that way. It'll just end up boiling. For this, we need to use electricity. Magnesium carbonate, if we simply heat that stuff, it'll break down into magnesium oxide and carbon dioxide. So again, sometimes our products here are elements, sometimes they are compounds, sometimes they're a combination of both. But the order is always the same. Reactant is bigger and more complex. The products are smaller and simpler. So another common example of that is hydrogen peroxide. Hydrogen peroxide will actually degrade in UV light to form water and oxygen. It's actually for that reason that hydrogen peroxide is stored in brown bottles to block out the light, so that this degradation process is at least slowed down by the container that it's in. That's why they don't sell it in clear plastic. Based on its shelf life, it wouldn't have very much of one. Light gets in, breaks it apart, you open it up, it hisses, and basically you have a whole bunch of water in a bottle that you paid a lot more for than you should have. All right, we'll end today talking about the replacement reactions. So single replacement reaction, this one's kind of interesting. What we have in a single replacement reaction is we have an element given here by our letter X reacting with a compound and the results of that reaction, the element kicks out the compound, or kicks out one of the ions in the compound. We get a new element and a new compound. Now, this always occurs with ionic compounds. You don't see this very often with covalents, but either side of the ionic compound can be affected. It does not have to be just the metal kicking out the metal. Non-metals can kick out non-metals as well. And that's evidenced by the two different reactions we have. So in the first one, the magnesium kicks out the nickel to make new compound and elemental nickel. In the second one, the iron kicks out the copper. So we get a new compound and copper metal. In the third one, we've got bromine kicking out chlorine and giving us elemental chlorine as a result. Now, I will stress, these are theoretical reactions. Actual single replacement reactions are governed by something called the activity series. The activity series is a list of reactivity. And the only way that an element can kick out another element is if it is higher on the series than the element that it wants to kick out. So that last example with the chlorine and the bromine, that wouldn't actually happen. Because even though we can't see it, it's not on this particular one, chlorine is actually higher on the activity series than bromine is. So as a result, bromine won't kick out the chlorine. It'll kind of just stay where it is. So the activity series helps us to govern whether or not a reaction will occur based upon the reactivity of the substances involved. So with double replacement reactions, we saw single replacement at the end of our lecture on Wednesday. Double replacement looks very, very similar. We're talking about ions changing places. The difference is, instead of having an element and a compound where there is the switching taking place, we've got two compounds, two ionic compounds to be more precise. And these ionic compounds are going to basically do a partner switch, where the cations, in this case A and B, are just going to swap places, reassociate. Now, this kind of chemical reaction is usually accompanied by some sort of visual observation. So if you're doing this experiment, you usually see the formation of a solid or the formation of a gas or some kind of heat evolution coming out as a result of one of these reactions. These reactions all occur in aqueous solution. They don't occur really outside of the solution. And they're unique in another couple of ways as well. And when we get into solubility rules and net ionic equations, which is next chapter, we'll see even more about kind of the things that govern these reactions. When they do form a solid, the solid that is formed in those kinds of reactions is known as a precipitate. Precipitation reactions are given to those compounds that follow that kind of reaction. Now, like I said, that's not the only kind of double replacement. There are others, and as we come to them and as they become relevant to us, we'll acknowledge them as they come. But most of what we see is that precipitation reaction. The last kind of chemical equation is the combustion reaction. Combustion reactions involve the use of hydrocarbons. Hydrocarbons are molecular compounds made up of only hydrogen and carbon. These are most often organic compounds. And when they react, the combustion reaction always follows this form. Hydrocarbon plus oxygen makes carbon dioxide and water. what's basically happening in these reactions is that the oxygen is inserting itself into the compound. It's reacting with the carbon and it's reacting with the hydrogen, both separately, but at the same time. Now, what this means is that there are other kinds of combustion reactions that actually exist where we aren't dealing with hydrocarbons. So, for example, if I had ammonia here and it reacted with oxygen, the oxygen would do the same thing. We would get a nitrogen oxide and water in that case. Now, as far as this proficiency is concerned, we don't need to worry about anything other than hydrocarbon reactions. That's why we focused on them. But understand that there are other kinds of combustions that can occur. Combustion is a general blanket term that is used for oxidation of substances that involve fire. So when we burn metals, those are combustion reactions as well. When we burn compounds that are molecular, that are not organic, those are combustion reactions as well. You did the empirical formula lab. Part of that lab was that the sulfur inside of that crucible burned off. There's no hydrocarbon there. It's just sulfur. Sulfur plus oxygen made sulfur dioxide. That is a combustion reaction. You could even see the flames coming out of that crucible as it did. So combustion reactions are not limited to organic compounds, but organic compounds are the most common type of combustion reaction. And balancing them out, you use the same kind of process. So we're actually going to skip this question. I just want to do a quick review, about a minute each for both of these. So get your answers in quick here. Which one of these four is a decomposition reaction? All right. All right, 15 of you are correct. It is the first one. Remember, decomposition reactions are where we have a single reactant and it breaks apart. The other two reactions, this first one actually has its foot in two doors. We could either call this a synthesis or a combination, or we could call this a combustion because we're dealing with oxygen and basically the burning of magnesium. Second one, this one's definitely a combustion reaction. All right, let's take a look at another. Okay, this was a little bit different. You can choose multiple answers here. What we're looking for are combination reactions. All right, let's see how we did. All right. Most of us are on the right track, assuming that all 16 of you that chose B also chose C. So A, that's a combustion reaction. Again, the difference there is that we have multiple products. If it was a combination reaction, we can only have one product. It's a synthesis. We're bringing together multiple things to make one single entity. Letter D is a decomposition. It's the one that we just talked about. Breaks apart. B and C, B is definitely combination. We're talking about two compounds coming together to make one. C, again, we can make an argument that it is combustion because of the oxygen, but it's definitely also combination since we have a single product. All right, any questions about reaction types before we move on?